Hi, I'm Kensuke Taguchi. I introduce our work, Uncertainty-Aware Interactive LiDAR Sampling for Deep Depth Completion. This is joint work by Kyocera and Chubb University.
LiDAR is a key sensor for 3D sensing that can be used outdoors, has a long measurement range, and has high measurement accuracy. With the evolution of LiDAR technology, solid-state LiDAR that is cheap and capable of programmable scanning has appeared and enables us to realize high-speed depth sensing because the operation speed of the LiDAR depends on the number of scan points. Figures show our prototype of programmable scan LiDAR and use case example. We talk a motivation of our work. The goal of our work is studying scanning strategy of programmable scan LiDAR for depth completion. Why is the scanning strategy problem called LiDAR sampling? We can simulate or train scanning strategy as sampling problem from dense depth map using RGB if both sensors are aligned on the same optical axis. In hardware implementation, sampled coordinates can be used for determining scanning position. We explain related works briefly. There are several approach non-learning, end-to-end, and active approach on recent works. Major drawbacks of related work are optimality and redundancy. End-to-end method is difficult to perform optimal sampling because sampling is a fundamentally non-differentiable problem. Active approach can assess sampling candidate in model output and shows good performance. However, it needs many iterations involving the inference process and it is very costly in terms of operation speed. Our LiDAR sampling is an interactive method to the depth completion module state. Conventional active approach needs iterative depth completion module inference to update module state. It is effective for optimal sampling, but very costly for operation speed. In contrast, our method is also interactive and need not iterative inference by virtually updating the uncertainty. A key component is candidate assessment module as an approximate function of candidate assessment to virtually update the uncertainty. Our definition of candidate assessment is very simple. We calculate candidate assessment table from the difference between depth completion uncertainty with blank depth map and with single depth point using already trained depth completion module. Next, we can train candidate assessment module with dense candidate assessment table as ground truth. Since it is created by the uncertainty of depth completion module, we think of candidate assessment module as a form of the depth completion uncertainty distillation. Let's see the results. We show the performance of depth completion compared with other LiDAR sampling methods on KT dataset. Because our method is for programmable scan LiDAR that is not high-end model, we set the target number of sampling depth points as 512. It is very low density compared with general depth completion setting. Our method achieves better performance with few numbers of key component executions. Next, we show some qualitative results. Our method mainly sampled LiDAR points on difficult area, like far or complex objects. Thus, depth points on the easy area like near road are not sampled. Compared with adaptive LiDAR sampling, our method can prevent the sampling results from becoming too dense on one area by interactive approach. To understand the impact of our sampler, we evaluate the result without our sampler. Without our sampler means depth points are automatically selected in order from the largest regions on the depth completion uncertainty. The performance without our LiDAR sampler obviously degrades, and sampling pattern becomes too dense in high uncertainty areas. Theses results show the importance of the interactive approach.
Thank you for attention.